All right, dissociation. Sometimes it's called disassociation. You might see it as that as well, but dissociation. So basically today we're going to talk about the breaking apart of ionic compounds into their ions. So when we separate ions in an ionic compound, we call that dissolving. And dissolving typically takes place in water. So in this first example, you see the potassium sulfate, and we put plus water almost as a reactant, but notice it's not present in the products. That's because it's not a reaction taking place. Dissolving is not a reaction. It's the breaking apart of a soluble compound. So when potassium sulfate is added to water, it breaks up into its ions. It breaks up into potassium, which you see as the first product, and then sulfate, which you see as the second. Ions are always aqueous. Ions don't exist in a solid, liquid, or gas state. They can't just float around by themselves. They have to be dissolved. And aqueous, the AQ subscript, this AQ state of matter, means that it does dissolve, that it is dissolved in a liquid. So all ions will be aqueous. So that's an example of a dissociation equation. This is another way, number 2 is another way to write it. And honestly, this is the way I sort of prefer to write it, with the H2O over the arrow versus putting the H2O before the arrow. Here are the general solubility rules. You guys don't need to memorize these, but you are going to have to access them a lot of times. So I suggest that you either take a screenshot of this slide or just save this slide at least somewhere. It is also in your book on page 413. So you can always access the rules from there. You're going to need these rules. And what they do is they help you determine if something will be soluble. So will you be able to dissolve it in water? So it does take you through like general ions here, general associations. So anything with a nitrate is soluble. Anything with an acetate is soluble. The only exception is silver acetate, which is only moderately soluble. So it still will dissolve, but not completely. Chlorines, bromines, and iodines are soluble, except, and that's why these are so long, is a lot of these do have exceptions, which is why I won't make you memorize it. I won't make you memorize those exceptions. But silver, if it's bonded with one of those, lead or mercury, they will be insoluble. That means they won't dissolve. And then there's specific rules like this one where it says lead to chloride, slightly soluble, but only in cold water, moderately soluble in hot water. So those are good examples of times when you would need to reference these solubility rules and really read and see like what the temperatures are and I don't know, stuff like that. So there's rules for all of these, and this is how you would use them. Typically, we use them for determining if a reaction is going to have a precipitate. This happens in double replacement reactions. So what we're looking at when it says like choose an example down here in this box is we're trying to see if any of these products would create a solid, or would they all be aqueous? Would they all be dissolved in water? Would they all create ions once dissolved in water? So we're trying to see if any of these are insoluble. So I can see that sodium is in every single product. And if I go back to those rules, sodium right here, this very last rule, all salts of sodium are soluble, except several uncommon ones, which aren't even listed because it's very, very rare. Oops, wrong direction. Those are all soluble. So I'm really looking at this barium one. Water doesn't count. Of course, water is soluble in water. That doesn't even really make sense. But these other ones all have barium, and they're with iodine, nitrate, and sulfate. So I'm going to go back and check out iodine. What was the other one? Iodine, nitrate, and sulfate. Sorry. Okay, so iodine, there is no exception for barium. So that means that barium iodide would be, that means that this one is soluble. So this reaction would not create a precipitate. Therefore, it's not a precipitation reaction. This one would not create a precipitate. So let's check out barium nitrate. When I go back and I look at the nitrates, up here, all nitrates are soluble, so that would also not create a precipitate. So let's see if sulfate will. And I come to sulfate. All sulfates are soluble except, barium. There we go, barium sulfate. This would create a precipitate, which means that if I mixed these two compounds together, they would most likely be liquids. I'd mix them together and I would produce a solid. That's what a precipitation reaction is when two liquids combine to produce a solid. We do what we write what we call a net ionic reaction. So a net ionic reaction is the actual reaction that's taking place to create the precipitate. So here's my chemical equation. I have sodium chloride, which is aqueous. I know because if I go back to my rules, right, all sodiums are soluble. And then up here for chlorine also, it says all chlorines are soluble except in these instances, which sodium is not one of those. So sodium chloride is aqueous. I would look at those rules. I could see silver nitrate is also aqueous. Looking at those rules again, we know nitrates are always aqueous. We also know sodium, again, always aqueous, or always soluble, sorry. But then we get here to silver chloride, and we go back to our rules and we would say, okay, chlorines are soluble except with silver. And so I would see that it's a precipitate, and they write it by putting an S. So the S indicates that it's a precipitate, it's solid. Anything that's soluble, you write AQ for. So insoluble gets an S, soluble gets the AQ for aqueous. So our total ionic equation, anything that's aqueous, because this is all happening in water, that's why I like to put the water above the arrow versus adding it as a reactant, because I think it reminds you to know that they're turning into ions, but also that it's not part of the reaction, it's just the facilitator. So my sodium chloride will break up, so I have my sodium ion and my chlorine ion. Oh, side note, you would need to balance this, but it is already balanced. Next is my silver nitrate. My silver positive ion and my nitrate negative ion, again, get broken up. And then I would break up, again, my product. So my soluble sodium nitrate, the aqueous one, would get broken up into the sodium and the nitrate. And then finally, my silver chloride does not get broken up because it's not aqueous. So it's not going to form its ions. It was insoluble, which means in the water that this whole equation is taking place in, this is the only thing that's going to be a solid. Everything else will be in its ionic state. So that's our total ionic equation. Sometimes we see it as full ionic equation. It's the equation that has all of the ions present along with the precipitate. And then what we did is we kind of thought of this arrow as an equal sign. And if the ions showed up on both sides, they got crossed out. We call those spectator ions. Those are the ions that are there to facilitate the reaction, right? Sodium had to be there because chlorine had to be bound to something before we put it in the water. And nitrate had to be there because the silver had to be bound to something before we put it in the water. And so when they got produced as ions, they stayed exactly the same. Nothing happened to them. No reaction took place for the sodium ion or the nitrate ion. So we call those spectators. We cross them out. And then our net ionic equation, again, it's the two ions that created our precipitate. So we have our leftover silver, our leftover chlorine, creating our precipitate product. So you guys will do a few of these. There will be some more examples in your notebook, as well as just practicing the dissociation. Let me go back to the dissociation slide one more time. So again, we see that potassium is being broken up into its ion and sulfate is being broken up into its ion. We will be practicing that as well, and you guys will see some more examples in the notebook.